Hello everyone, I'm just going to do a quick little discussion about Chapter 9, Foundations. So I got the notes right here in front of me, which you can see on the document channel. And then I have the PowerPoints here off to the right here. So first thing, foundations are subject to greater structural pressures, water, moisture, loads than above grade structures. So they're basically acting as a retaining wall, stopping water from getting through, and moisture from kind of going through diffusion. So lots of things that have to be taken into place. So they have to be able to carry the weight overhead, stop the moisture, stop the building from collapsing towards the inside because of ground pressure. That being said, moisture problems are obviously an issue in basements. They always feel a little bit more damp and moist, cooler. So more potential for mold. People have kind of tried to take that space and utilize it as a living space, but expect the same kind of results as you would have on upper floors. So we got to kind of change the way we construct those floors or that basement to make sure that that you feel more comfortable. So more use of styrofoams on the wall for insulation, more use of styrofoam underneath the slab would then make the space feel warmer and not as damp. So that's kind of what we're going to look at as we go through. Another item I have right here, so foundation basement problems can be expensive to fix, special attention to design. So making sure that the footings are the proper size, following the plan, right? So the architectural technician will come up with those numbers whenever they actually design the plan, and then from there it's built accordingly. So making sure there's rebar in there, make sure there's a soil test done to see what kind of bearing capacity the soil has before you put the footing in place, making sure that there's no roots, or so you're on undisturbed soil. Make sure there's no water table right underneath the footing. And if so, you have to oversize the footing, all those kind of things. So a plan will tell you one thing, but then once you get onto the job site, you actually have to physically look at the soil, do a test hole, not where the foundation is going to be, off to the side, and then from there, figure out from an engineer's report what you need to do. So moving on to the next slide here. So this is kind of just looking at the pressures, right? So possible cracks, ground pressure. If moisture gets into the foundation, it wants to work upwards and then rot out our sill plate. So if we can protect the exterior with damp proofing, that stops moisture from getting in and traveling upwards through capillary action and then rotting out the sill plate. So cracks, settlement. So if you're not on undisturbed soil, the foundation could potentially crack. Once you have cracks, more than likely the damp proofing is going to have holes into it, and then water will be able to get in, up. So lots of potential problems with that. The slab, same idea, right? So having 3/4 inch clear gravel underneath the slab stops the moisture from getting into the slab, which then you feel that when you're in that environment, right? So if the slab is cold and damp, you're going to feel that. It's possibly also going to create mold on the underside of carpet. A lot of people still like to use carpets in the basement. It makes the floor feel warmer, is one reason. But by that being said, there's potential for mold on the underside. So having 3/4 inch clear gravel, having a moisture barrier underneath that slab, like a 10 mil poly, will stop that from getting through. Some people even put styrofoam underneath the slab. Again, that'll act as the moisture barrier, tape all the seams, and that'll give you R value, as well as a barrier, moisture barrier, to stop capillary action from occurring in the slab, making that slab much warmer. A couple of houses that I've worked on, they've run water lines through the slab in the basement. So if your feet feel warm, it's unbelievable how your entire body feels warm. So that's a pretty good advantage as well. So a lot of people will put styrofoam underneath, they'll run tubing that's attached to wire mesh like I showed you on the previous slideshow, and then they'll pour their concrete around that, and then they circulate water in those pipes, hot water, which then heats up the slab, making the environment feel nice and warm. That's basically radiant heat as well, right? If the concrete gets hot, it'll radiate heat to the room, making the whole room feel warm. So you wouldn't have to use as much heat source in the basement. Like a lot of people will have a forced air furnace in their house, meaning ductwork, and that supplies the upper floors. Usually, when the general contractor built the house, there's maybe 3 or 4 ducts in the basement. But whenever a homeowner buys that house and then starts putting walls up, all of a sudden, potentially some rooms don't have ductwork. So the odd person might throw in baseboard heating. That would not be needed as much if you have radiant heating in your floor. A couple of ductworks, radiant heating will make that room feel very, very warm. So we look at the notes here. Basement must provide structural support. Looked at that already. Control heat loss. So making sure it's insulated. We'll get into that a little bit later. Control air leakage and soil gases. So by having air barriers and sealing things, we then prevent the gas from coming through into the living space. Control in and out flow of water. So you can see the picture up on the power plates here. By controlling the water, so any water that collects on the roof goes into the east troughs, into a downspout, and then should be kicked away. This downspout here should be about 6 feet, making sure the water gets well away from the structure. You have to keep in mind that typically we will excavate about 4 feet from the foundation to be able to do the work that we have to pour the footing, get the drain tile in, get the gravel in. So you don't want to be dumping that water in that 4-foot trench, because that's probably not compacted like the rest of the earth. So if you can imagine having, if I drew a line right here, I don't think I can right here, but no, I don't think so. If I drew a line right through here, that's excavated, that's not excavated. That's going to be a lot more dense than this. So if I'm dumping the water into that excavated area, more than likely that's where the water's going to go. Water will follow the path of least resistance. So if this is more dense than this, it's going to get into that area. So we have covered that, right? The building industry has a 4-inch drain tile beside the footing, has gravel there. So if any water were to get in this area, it gets into the gravel, then into the drain tile, and then from there it goes to a storm sewer or to a sump pump. And then that area is dry. The biggest thing is if you have lots of rain. So heavy rain coming down, maybe the system can't keep up. So if you take the water off the roof and get it away 6 feet away from your building, you don't have to worry about clogging your weeping tile with all that extra water. So it's just trying to not put water where it could potentially be a problem during a storm. On a regular day, not an issue, but just during those storms, or even in the wintertime when we get the freeze-thaw cycle, you can have an excess amount of water. You might have a big pile of snow right here. Usually that snow melts close to your house because you're losing heat. When you lose heat, it melts the snow. So we have a big mound of snow right here, and all of a sudden it starts to melt. Water starts to pool. It's going to start falling on that foundation. Again, the ground is frozen, so there's frost in there, so it's going to be forced against the foundation wall. And if there's any issues, it'll kind of get through that foundation wall. But the whole idea is eventually it'll make its way to the drain tile and then get away anyways. But just things to think about. So foundation needs to meet code requirements, so size properly. Spec for sound and fire, so if it's made up with ICF foundation, so insulated concrete forms, that have to be covered with drywall to prevent toxic fumes from entering the house. Be economical but durable, so concrete is a lot more durable. Other foundations are made of cinder block as well. My house is made of cinder block. That's something that I don't prefer, but long as the ground is maintained and damp proofing maintained, it shouldn't be an issue. The key is keep the water away from your foundation. So downspouts kicked out. That's a kick out, right? Downspout kicked out. Make sure your land is sloped properly away from your house. Don't water your flower beds right up against your house as often as you probably do. Try to reduce the water that's against your foundation. So flower beds against the foundation, not a good idea. They are nice, but just don't overdo it with water. Okay? So if it rains, don't water that night. Leave it kind of percolate through the ground on its own. So here, water moisture can enter through several ways. So figure 9.1, we already looked at that. No, that's the one right here. So from concrete, still in the curing process, capillary action and diffusion through the wall slabs, condensation from warm, humid summer air, and through cracks in the foundation wall. So condensation in the summer, right? We have maybe we're AC in the basement, so it's really, really cold. And then the hot air from outside tries to work its way inside. Whenever that hot air reaches a cold surface, it turns into water, right? It reaches the dew point. And usually that's right on the inside of the foundation wall, right? So the heat will go through the concrete. The front face of the concrete's hot because of the sun. It travels through the concrete, reaches a cold surface, so it's probably the inside of the concrete, and then from there condenses. So we have water trapped in the basement. That's why it's smart to have a smart vapor retarder in the basement. If any water gets into that assembly, it's able to evaporate into the basement through the smart vapor retarder. That's why the tar paper is there. Moisture comes from the exterior in. We don't have moisture issues in the wintertime with condensation. It's in the summertime. So it's coming from heat, which is outside working towards the inside, is the problem. So smart vapor retarder preferred in basements, not 6mm poly. Water moisture can be damaged by figure 9.2, so proper surface drainage, so making sure you have proper drainage coming away from the building. So 6 inches in 10 feet, so 5% slope. Free drainage backfill, so if you can, free drainage backfill would be sand. So again, 4 feet out, draw a line. If you backfill all that with sand, the water will get through that quickly. The key is to have the downspout beyond the sand, to make sure you're not dumping all the sand on the roof, or not dumping on the roof into the sand. So if your sand is at 4 feet, make sure the downspout goes 2 feet beyond that to make sure the roof water is on the ground. So ground with grass is dense, so the water will travel on top of the ground if you have it sloping. 5% grade, okay? Filter fabric protected perforated drain pipe, right? So at the bottom, we talked about that already. Insulating from exterior. So if you are going to insulate from the exterior, let's just see if there's a slide link to that. So here, that's an ICF foundation, styrofoam on both sides. A lot of people put styrofoam on the outside, right? So this is your foundation, styrofoam on the exterior, nothing wrong with that, but you got to make sure that your concrete has cured. So usually 28 days is what you need for proper curing. They say concrete never cures 100%. So usually probably a week of opened to the air would be a good idea. Then you can install your styrofoam. It can still dry towards the inside, as long as you don't finish the inside right away. So that's just to allow the moisture to escape out of the concrete so that it's able to cure properly. Exterior foundation insulation will reduce inside wall condensation. So if we keep basically we're kind of keeping the concrete warm, right? So the ground is cold. We have moisture coming through with heat, and it hits a cold surface. So by having foam on the exterior of the building, it's keeping that concrete a little bit warmer, trying to reduce that condensation from occurring. A lot of people nowadays will then add another layer of foam on the inside of the building, again keeping that concrete warm. If we keep that concrete warm, any moisture traveling from the exterior of the building toward the interior won't reach the dew point until it gets closer to the inside of the building, and then that's not a problem. We don't want the condensation to occur in the wall assembly. So keeping the concrete as warm as possible will then push the dew point closer to the inside in this case. So condensation issues in the basement occur in the summertime. So you're conditioning the air in the basement, making it cold, hot air from the outside traveling inwards. So kind of the reverse of what happens in the wintertime on our first and second floor walls of our building. So exterior insulation must function in wet conditions, so EPS, XPS, or rigid glass fiber. The one that's probably used there the most would be XPS, but then again, ICF foundations are made of EPS. You also have to make sure that your damp-proofing material is compatible with the foam. Some damp-proofing materials would eat right through the foam. So any petroleum product on foam tends to just kind of melt the foam. So picking the proper materials to go with your foam is very, very important. You also want to protect that styrofoam from getting breakdown from whenever you're weed eating your lawn, cutting the grass around your foundation. So a lot of people will then stucco that foam, making it rigid. That also stops rodents and termites from eating their way into the foam and then working their way into the building. You can see on this particular picture we have up on the screen here, if a rodent were to get into here, they're basically getting into your house. So you'd want to make sure that you put some kind of a wire mesh and then a stucco finish on that foam afterwards to maybe make it simulate concrete. But the key there is making it strong so things can't get through it and then deteriorate your house. Another thing is making sure that the foam is fastened to the foundation wall so that frost doesn't grab onto it. Like if you can imagine this foam heaving up, so frost goes into the ground and eventually it wants to lift. So if it lifted, lift up on this foam. If it lifted up on the foam, it pushes up on the siding. That's called ad freezing, when when frost grabs onto a material. So the frost will freeze to a material and then push it up. That's why it's important to have damp proofing in the drainage layer. The drainage layer a lot of times kind of creates a separation between the frost and the foundation wall, like a buffer, if you will, that allows it to kind of move independently. Poor soil conditions. Let's go back here, make sure I'm not missing anything here. There's some drain tile kind of explaining the sump pit. There's the pump, water goes in, goes out, and towards sewer, or it could go right directly towards the storm sewer here. So poor soil conditions are questionable. A geotechnical engineer should be consulted. Complete waterproofing system available when groundwater tables are high. So if you live close to the river, you might have to have your foundation waterproofed. We damp proof a foundation, right? But if you're in a floodplain, so floodplain meaning if you're beside a river in the springtime, that river overflows, floods if you will, and that flood comes onto your land and surrounds your house. Your house would then have to be waterproofed. So typically they won't allow you to build in those areas, but there's a lot of older homes that are in those areas, and what a lot of people do to try and get around the system is they'll leave one foundation wall standing and then build a brand new house off of that one wall in a floodplain, which is legal because they left one foundation wall up. It's kind of a glitch in the system. But a lot of times those houses should be waterproofed, meaning what we do to a foundation is just simply preventing water from going through one direction. Waterproofing means completely around the entire floor, right? So waterproofed on the side, waterproofed underneath the slab, like a gasket, making sure that no water can get into the structure. So very costly, but if you're going to be close to the river like that and susceptible to flooding every year, it'd be a good way to protect your investment. So that is possible. Another thing, moisture content can cause, so if lots of moisture, so if you have ground that has a high water table, maybe it's clay. A clay, when it gets wet, it expands. So in some areas, the clay expands so much that it creates the slab to rise a little bit. And then once that soil dries out, it then shrinks, creating a gap underneath the structure. And then the structure is able to drop. That's why it's so important to have soil engineers taking a look at the ground prior to putting a footing on top of the ground. That way they're responsible, they understand, and they have all the experience and the know-how to make sure they realize what kind of soil that is, and from there take the proper precautions. So in some cases, it's continuing to dig until you get rid of the clay. You might have to bring fill back in, or so maybe if there's an extra foot of clay, remove that foot of clay, bring gravel in to elevate it back up. That gravel will be compacted. So moving on, they're just kind of showing an ICF. So there's a membrane that's compatible to the EPS. That would be EPS foam. These yellow things here are your ties. So on a regular concrete wall, that'd be metal. You can see there's some rebar sticking out. But these are basically ties that hold the foam the proper distance apart, so when the concrete goes in between, it can't spread. But then they're also used as a location to screw your drywall on. When you go to put drywall on the inside of the building, you put your screws into these little yellow caps. They're placed 16-inch on center, just like a stud. So there's no need to frame a wall on the inside of an ICF foundation because it's already done. You can see they have a nice chunk of foam underneath the slab here, making that slab warmer. There's 3 rebars in the footing. You can see that damp proofing coming down onto the footing. You can see a metal track here. So they actually use metal track for steel studs. That gets tapped on or hilted into the footing. Then the ICF foundation sits into that track. That stays there. Damp proofing goes on top of that. And then here's the plating system. It's white on this drawing, but we discussed it. It was a black membrane that gets nailed on. So that's your damp proofing. That's also damp proofing, but also a drainage layer. And then your weeping tile down by the footing, covered with gravel, and there's your backfill. So you can see this is styrofoam protected. There's probably a concrete board here, and it looks like stucco. So then when you're cutting your grass or weed eating your grass, you're not damaging the EPS foam. Okay? You can see the damp proofing above grade. Okay? So here's more scenarios of the styrofoam. You can see foam on your slab, foam on the side of the slab, so creating a seal but also insulating. If the foundation moves, the slab doesn't move with it. That's a big issue. Sometimes when you pour the slab directly against the foundation wall, it adheres slightly. It's still a cold joint, but it adheres. For some reason, if the foundation went up or down, the slab would go with it, causing the slab to crack. So by having a buffer, a material that's flexible in between the two, which is called an isolation joint, that allows this material to not move when this material shifts. It shouldn't shift, but things happen, right? You could have ad freezing. Maybe you have a carport right here. Lots of water getting into that carport because the ground not sloped properly. So if the frost grabs onto that foundation, it might heave it up. So if the slab were not isolated, then you could have a problem there. This is showing a standard foundation. So foundation damp proofing, weeping tile. We've got tar paper nailed onto the wall with a strapping with concrete nails. That gets put in place to grade. And so moisture damp proofing to grade. And then from there, your bottom plate, typically there's a piece of plastic installed underneath of your bottom plate. And you got to make sure you don't drop your moisture barrier into that plastic, otherwise you'll collect water at the bottom. You can see it curls around, and then you have a studded wall. Insulation in the floor system comes flush to the basement wall, and we put a vapor barrier in front of that. Okay, so you can see some adhesive at the bottom. Seems like the drywall here might be the air barrier in the basement. Okay. An area with brick, so they have a flashing that's required by code under the brick. Why? Because capillary action, right? Any water from the foundation, if it were to get into the brick, first thing it would do is discolor the brick, but it would also get water into the brick. Once that water freezes, the bricks will blow apart. So you need to have a flashing there. There should be a 1-inch space in between the brick and wall to allow any water from above to get out. We also want to stop the water from coming from below. But here you can see the membrane continuous, right? There's your rim wrap. They have it on top of the sill plate, which is nothing wrong with that, but it's just hard to see your layout lines for floor joists. That's why most people put it underneath, so you can do your layout lines on the sill plate. You can see the layer of styrofoam on the exterior, creating continuous insulation. no potential for a thermal barrier or a thermal break, right? I mean, you can't have a continuous path. So a pretty good idea. See here they have a little bit of bad insulation and a little bit of foam. And they've caulked around the perimeter of the foam to create a seal. Here's some more pictures there in the basement. So insulating over top of a window, styrofoam sealed, so that more than likely being the air because it's being sealed. You can see your tar paper on the foundation, bad insulation. Okay. So vapor retarder, your bat insulation studs, rigid foam. So it looks like they put rigid foam on the back wall here, which is a good idea. Probably the best solution is gluing on rigid foam. I think I showed these pictures, I think it was 2 weeks ago, when we talked about foundations a little bit, but that's your standard minimum code a few years back, the bag that gets stapled off across the bottom. You can see that's being removed, and then basement walls are being put in place. And then from there should be tar paper or a moisture barrier of some sort from basement slab up to grade installed, then insulate, and then so forth. Smart vapor retarder, and then a drywall finish if whatever is going to be put in place. The better option would be styrofoam glued on, seams taped. That could be your air, right? And then from there you can install a studded wall in front of it. I prefer to see a rock solid insulation in the basement, and then maybe a smart vapor retarder in front of that to not trap moisture. So this is fiberglass and 6 mil poly. So rock solid with a smart vapor retarder would be my choice, with the foam behind it. So you don't even see the foam. So the foam acts as an air. It also gives you more thermal and a moisture barrier. So I would still keep a gap between the foam and the wall of about 1 inch for any moisture potential that could build up there from condensation occurring in the summer. Okay. Here's spray foam in the basement, very good idea as well. Costly, but a good option in the basement. Any kind of a bad insulation, such as fiberglass or rock salt, might take on moisture. And then from there, hold on to it for a little bit and then spread it into the wood. Rock salt will dry out and be okay. Fiberglass is then garbage. So I would not use fiberglass in a basement for that reason. Spray foam being the best option, because if it gets wet, it's not going to really penetrate the material. And typically with spray foam, there's no condensation, like very little condensation unless you get shrinkage on the wood frame, which might allow some moisture to go through. But again, that material won't absorb the moisture. So it's not really a danger for mold. Okay, but it has to be fireproofed, covered with drywall, same as your styrofoam. It has to be covered with drywall, or a wall in front of it covered with drywall. So there's the old-fashioned way of from the general contractor, passing minimum code to then sell the house to a homeowner. They get the bag, no walls up, and then typically 2 years down the line, homeowner decides they want to start framing that wall. So then they'll rip all that out, put tar paper. So it's okay to go tar paper from bottom to top because it breathes. Just don't tape the seams. If you tape the seams, the tar paper might not breathe. So it's not necessary to go any more than above grade, but in this case they went all the way up. So it looks like they actually stapled the tar paper onto the backside of the wall, in this case. So again, you can see the gap behind the wall. So in this case they went 6.5 inches from foundation wall to stud. So they're probably going to install a R20 bat there, which is going to be 5.5 inches, which will still leave a 1/2 inch gap behind the bat. That's exactly how I do it. So if I'm going to frame a basement wall, I'm not putting 2x6s down there. I'm not going to put 2x3s down there. I find they're not strong enough. 2x6 is overkill. It's just a wall to receive finish. I don't want it to bow and cup and twist, so that's why I don't bother putting or crown. So that's why I don't bother putting 2x3s in the basement. I put 2x4s, but I offset it off the wall enough to make sure that my bat insulation fits in there with a gap behind it so it's not touching the moisture barrier. Okay, so exactly like that. Here's the slab we talked about a while ago. A slab with the radiant heating running through. So styrofoam underneath the slab, radiant heating on top of the foam. Usually it's onto a wire mesh, and then from there poured concrete slab, and then that floor will be heated. Okay. Kind of getting ahead of the notes a little bit here. So interior insulation. So interior insulation is cheapest, but more moisture problems. Three basic arrangements, so full coverage, heat, so less heat loss. So that goes basically insulation all the way to the bottom. Majority coverage, 8 inches from the bottom of the plate, protects footing. So a lot of insurance companies, let's see if I can find a picture of that. So majority coverage means the insulation goes right to the bottom plate. Majority coverage. So that's going to be your best scenario. Sorry, that's full coverage. Full coverage goes right to the bottom plate. Majority coverage is 8 inches up from the plate. So a lot of insurance companies, if you've had a flood in your house, that's what they'll ask for. So normally when you have a flood in your house, the insurance company will come in with something like a service master, like a restoration, and they'll actually remove 2 feet of the drywall, remove the insulation up to as high as where it is wet, potentially dry it out, put chemicals in there to clean it all up, or paint it to seal off those mold spores. And then from there they'll reinstall the insulation, but leave it 8 inches above the bottom plate. So if the basement floods, the key is the water won't get into the insulation and work upwards through capillary action. That's what's happening, right? So insulating right to the floor is best for thermal, but if it floods, the water gets into that insulation and travels upwards through capillary action, causing it to spread even further than it should have. Or if you left an 8-inch gap at the bottom, a little cooler, but you're not going to be grabbing onto that water and making it travel upwards. You see here, partial coverage, 2 feet below grade, SB12, remove this option so it's no longer allowable. So basement walls should be insulated to the same level as upper wall, so R20. If you look at the SB12 code packages, that's even going higher now. Sometimes there's continuous insulation, so R20 could be an R20 bat. But the code's actually requiring some areas or some packages to have a continuous insulation installed first, and then maybe a framed wall afterwards with like an R12 bat installed into it. So again, there's several packages in SB12. You got to look through them and then find that information, and then pick your whatever way you like to insulate. So insulation can be rigid board, spray-on fiber. Remember, curing concrete should be left uncovered for as long as possible. So usually when you're doing the basement, it's been a while. The floor's on, the walls are up, the roof trusses are installed, plywood's on, shingles are on, windows are in. All the trades are upstairs, and then you might go into the basement, start framing the basement. So at that point, it's probably a good 3-4 weeks down the line, if not longer. You can see here, wood framing can be thinner and held away from the concrete wall. So 1 inch space between the wood frame and foundation wall is bare minimum. But you also want to have a 1 inch space between the insulation and the concrete wall, so the moisture from the concrete can't get into the insulation. That would be bad. So like that slide I was showing right here. So it's a 2x4 stud, so 3.5 inches. There's a lot of gap behind there, but you're allowing for the insulation. So that's very, very important. You shouldn't be worrying about floor space. You're losing floor space there, but you want a basement that's going to be all moldy and unhealthy? No. So make sure you think, I need R20 bat in there. I need to have an inch gap behind that. So figure out what you're using for materials and allow for that. Interior moisture barrier is required between the concrete and wood insulation, so the tar paper to grade. Okay. It says right here, tar paper, could be house wrap, could be the bubble wrap, aluminum faced product as well, to grade. So depending on the product, if you go above grade, you're potentially not allowing that wall to dry out to the exterior. Just keep that in mind. So to grade is probably the best thing to do. That allows the top portion of the wall to breathe. if you bring that membrane all the way up and it's non-breathable, it can't dry to the outside. It can only dry to the inside. Most people put 6 mil poly on the inside, so it won't be able to dry to the inside. It should be a smart vapor retarder in a basement, so it can dry to the inside. But it's also good to allow it to dry to the exterior, because smart vapor retarder will only dry out if it reaches a certain humidity. Then the pores of the material actually open up and allow the moisture to come through. Okay, preserve wood foundation. So it says here ADA is an approach or smart vapor retarder. Right, maybe we should add that in. That hasn't been around for a long time, so these notes probably should have been updated, but add that in there. Then we get to preserve wood foundations. Let's skip this up. Oh, come on. That's a preserved wood foundation, so no concrete. The footing's actually wood, so it's oversized. It could be a 2x10 or a 2x12, and then it's maybe a 2x6 or 2x8 wall frame on top of it. Again, there's plastic underneath that, so there's a compacted layer, so granular drainage material put underneath, so 5 inches minimum. Footing sits on top of that, wall sits on top of that. So these houses are pretty popular in BC, but there is some in this area. Like I know my grandparents actually had a preserved wood foundation. They're no longer in that house, but it's still standing. Typically the house feels warmer. Why? Because you have insulation. Is it as strong? For a downwards pressure, yes. For inwards pressure, probably not until you get the slab. But you can see here, once all the foundation walls, or in this case preserved wood walls, are built, the slab gets poured in between them. So that stops the earth from pushing in at the bottom, causing this wall to bow in. So typically your slab or a wood floor is poured before you backfill. So it doesn't have to be a concrete slab. It could be a wood floor. Usually the wood floor is elevated a little bit to stop moisture from coming into it. So you basically put a ledger board on the basement walls and then floor joists tied off the ledger board. That takes care of that. You can see at the top of the wall here, they kind of showed a metal plate. That metal plate is a framing strap used on every second stud. So it's nailed into the foundation wall, curls on top of that, and ties to the floor. Why? Ground pressure. When you backfill, ground pressure might force that foundation wall to bow in. So that strap prevents that. So proper nailing of the rim board and the floor joist to the wall, as well as straps on every second stud. On the exterior, so typically it's plywood, so a preserved wood, so it's special wood, right? So it's not standard pressure treated. It's not the same wood as you would use on a deck. It's preserved wood, not pressure treated wood. It's preserved wood, so it's bought specially, made for that purpose. The plywood is the same way. So a lot of times the damp proofing on the outside is poly. You see here, polyethylene damp proofing. In this case, they also put a layer of fiberglass drainage board, so like the Roxol 1-inch board that I showed you in class 2 weeks ago. And then from there, they'll put a protective coating on top of that. So it could be a cement board or even plywood again to prevent those materials from getting damaged, the drainage layer and the damp proofing, which is 6 mil poly in this case. So a very decent way of building a foundation, cheaper, lighter. Contractors can do the entire building. So you don't have to sub out to a concrete company to pour a foundation wall and a footing. You can just build it all out of wood. Again, moisture, ground moisture would be a big factor to look at. Make sure you're out of the water table. Make sure you're up on a hill, not at the bottom of a hill, because water and wood don't really mix well. But if you have good drainage, you have the water table where it should be below the footing. This could be a structure that'll withstand just as long as a concrete one. It's all about maintenance and doing things correctly the first time. Okay? This is showing a crawl space. Just make sure we go through the notes here. Pressure tube, so it's called preserved wood, not the same as a deck, suitable for grade. All edges of plywood are caulked and sealed. 6mm poly used for damp proofing. Poly grade sealed by a piece of treated plywood that must extend 3 inches minimum above grade. So again, so it's for the weed eater to not make contact with it. Some people will then cover that again with a wire mesh and scratch coat it, make it look like concrete. Seal in between both both plywood pieces. So there's basically going to be a little joint. If this was your, if that was grade, there's your foundation coming out of the ground. They want, and then you have your damp proofing. They want to have a piece of plywood on top of that, minimum 3 inches above, and seal right on top of that, so water can't get underneath there. Backfill with sand is suggested for preserved wood. Okay, good drainage, get the water down quickly, so it doesn't go through and force against the foundation. 6mm clear stone drainage layer under the footing instead of a weeping tile. So go back to that. It's pretty good. So no weeping tile. The entire underside of that building is drainage material, granular drainage material. So if any water is to collect underneath there, it then gets pumped away. Okay, so you probably have a sump pump somewhere. All that water will flow into that sump pump, and then from there diverted out. Okay, so the entire building is basically a drain tile, which then directs the water into a sump pump or to the sewer. Crawl space. So looking at different ways of doing a crawl space. Shallow foundation, so there's low headroom used where high water table exists, where frost line is shallow, so maybe rock or something like that, so, or bedrock close to the surface. Okay. Should be heated. Treat as a low height basement. Insulate the perimeter and the headers. Could be used then for storage and mechanical. So that's kind of the ideal situation. Not everybody wants to do that. If it's unheated, it must be ventilated. So there's pretty good information on that in the textbook, which you should be reading the chapters. So if it's unheated, it must be vented. So unheated would mean that the floor is then insulated. The floor joists, in between all the floor joists, would be insulated. You'd have to treat the floor like a wall, right? So whenever you insulate a wall, you do the same membranes as though you're doing it on a floor. So if the wall needs a air, thermal, moisture, and a vapor barrier, the floor needs the same thing. So the floor needs air, thermal, vapor, and moisture. So you're going to treat it the same, think the same, put all the membranes through the same. Sometimes the plywood, if glued on all joints, can be considered as your vapor barrier. So that's one barrier taken care of. Then you could insulate in between the cavities. If it's a crawl space, I would suggest doing spray foam there. Again, doesn't take on any moisture. From there, you can then install sheathing underneath to create a solid barrier so rodents can't eat through it. And then from there, maybe styrofoam, and then tape all the seams, and then that could be your air and moisture. So that styrofoam, again, you'd want to be breathable. So on EPS foam, if you put EPS foam on, maybe 1.5 inches thick, you could cover that with Tyvek afterwards. Or buy a product that has EPS foam with a membrane on top, such as Isoclad, and it's a one-shot deal. So if I'm going to use foam, I might put the foam on first and then cover the foam with plywood to then make sure that rodents don't get into the foam. But that's taking care of the floor like you would a wall. It has the moisture barrier, the air barrier, thermal, and vapor. Okay? That's the ideal. Ideal scenario if you don't want to heat the crawl space. Heating the crawl space is the best, because then all your wood is exposed and allowed to air and dry out. So in that case, you actually insulate the perimeter walls and then insulate the floor. You see here they have a 6mm poly sealed, so moisture can't come through. So they might pour concrete on top of that, or they might spray foam that. See, now they have that bubble wrap on the foundation wall perimeter, but they won't insulate the floor system. That's left wide open. So insulate the floor of the ground and the perimeter walls. Okay, so the dirt, if you will. I think it's a good idea to put 6 inches of gravel, even though it's a crawl space, just to keep things clean and keep the moisture down. And then a poly on top of that. And there's also slab on grade. So foam being placed typically at the perimeter and up the walls to stop frost from coming through on an angle here. And then styrofoam underneath the structure as well, stopping frost again from coming through. Slab on grade, usually it's thickened at the edge because that's where all the weight's going to be. So the center of the slab is thinner because there's no weight there. Come to the perimeter, that's where the weight of the walls, trusses, shingles are bearing down on top of what we usually have a footing there. So it's thickened with rebar at the edge, but still has to be protected from frost. See, there's a weeping tile there to get rid of the water if it collects. So lots of gravel underneath, so clear gravel to get the water away, or it could be compacted, depends on the engineer. Okay, so in this case they're saying granular layer of compacted gravel. Okay. So slab on grade. This is kind of what they call a frost wall. So it's a small little knee wall, footing, foundation. It can't go in the ground too deep because maybe there's rock there, but the footing is not below the frost line. So if the footing is not below the frost line, the frost can actually push up onto it. Right? So ideally what you want is if that's your slab, there's your foundation. In our area, the frost goes down 4'6", is what they say, right? So frost starts from the top and works its way down. So ideally, we want to make sure that the bottom of our footing is below the frost line. Because if we stopped our footing here, and the frost went below it, frost then pushes up. It's like a Pepsi can or a bottle of water in a freezer full of water. Put the cap on it when it wants to explode. So that's what happens when the water freezes in the ground. Everything wants to push. So it pushes upwards, pushes sideways, pushes down. So if the frost gets below the footing, it's going to push it up. So that's what happens potentially if you have a rock or high water table. You can't go any deeper. So then what you have to do is you have to protect the footing and foundation from frost. How do you do that? You put foam on the foundation wall. Foam usually about 4 feet out from the footing to stop the frost from coming in, right? Frost will come down and it wants to curl underneath. So if I have a piece of foam here, that stops the frost. A good little test in the wintertime is to throw a piece of styrofoam on the ground, let it snow, so put something on top of it so it doesn't fly away. Let it snow, maybe go back in January or maybe even February. Move that piece of styrofoam, so make sure that piece of styrofoam is like 4 feet by 4 feet. So if that styrofoam is flat on the ground throughout the winter, stops the frost from going in, because frost starts from the top and goes down into the ground. So if you move that piece of styrofoam later on in that winter and then excavate in the center of that styrofoam, the ground should be somewhat soft there. Keep in mind that the frost will try to kind of curl around. So that's why having a 4-foot piece of foam will make that test work more efficiently. Otherwise the frost will curl in and it'll still feel pretty stiff on the edges, but in the center that ground will be fairly soft that you can dig. Same idea, that's why we put the footing out here. So the footing goes out enough to make sure frost can't come around and get underneath and push up. So that's how it's dealt with if the footing can't go below frost. So if it can't go below frost, that's the scenario you have to do. Ideally, you want to have that footing below frost. Okay. So that's all pretty well outlined right here. You want to make sure if you're putting foam underneath of a footing that it's structural. So there's different types, type 2, type 3, type 4, that'll actually are made for density, which then can actually take the weight of a building. So using the proper XPS foam, so you can actually put foam underneath the footing as well. That'll help with capillary action, that'll help with warming things up, stopping heating, right? Stopping heating from occurring. Okay? Like when I do a garage, even though it's not potentially going to be heated, I put styrofoam underneath the footing here. So I put foam here, usually to about here, and then from there I just follow through with the aluminum foil paper. And then, so I got a little bit of foam here, foam here, foam here, and then up the side a little bit. On the outside if it's going to be heated. So I'm just trying to protect that. So even though it's not heated, it's going to take on frost. It's all going to move together. Just as a precaution. So here, same kind of a thing if you put piles in the ground or sonotubes. So this is actually a wood pile. That's a metal pile. There's a new piling system. It's been around probably for about 10 years. That's called Technopost. When they first came out, Technopost has a big auger-like style bit at the bottom, and it's attached to a pipe, and there's a machine that actually turns that into the ground. That'll stay there, so that auger section stays in the ground, and then they put a saddle on top that'll then receive a beam or a post, and you build your structure on top of that. So when that first came out, they just put the metal in the ground, and then obviously they ran into some problems. Now they put a green sleeve around the metal. So basically what that's doing is creating an isolation joint for ad freezing. So ad freezing, so frost, water in the ground will then freeze to the pipe. So if the frost grabs on the ground and pushes it up, the pipe will go with it. They do have that propeller-like auger at the bottom that stops it from coming up. That helps. But by having the sleeve go around the pipe, the sleeve will move, but the pipe won't. So the sleeve will adhere to the frost, but the pipe won't. So same thing they're doing here, right? So if your frost depth goes down 4'6", protect that area with a sleeve of some sort. So asphalt, impregnated paper, Tyvek, 6mm poly, something that'll not allow the ground to freeze to the pier, if you will. Construction nowadays, if you're building a deck, you'll have a sonotube. So a sonotube is a circular cardboard form, and at the bottom of that is usually a big base, which they call a Bigfoot. Right? So if I draw it here, it looks very similar to a foundation, but so you have a sonotube, which is a cardboard tube, and that adheres to a Bigfoot. There's two separate pieces. You buy that separately from this. You join the two together, and then you pour concrete into this tube. The concrete will go into the Bigfoot, and then you backfill. Usually the slab or sonotube's out about 8 inches out of the ground, so you don't rot the wood. But if frost were to adhere, so again, this footing here should be below frost. So I usually put that down about 6 feet or so, just to make sure, 5 to 6 feet. Frost is 4'6". But there's these kind of like knobs, if you will. So if the frost were to grab onto the sonotube and try and lift it up, you're then trying to pull all this ground here up. So in the old days, what they used to do is just use a straight tube. So if the frost grabbed onto that, it would come right out of the ground. So by having these knobs, it stops it from coming out. It also acts as a footing and a snowshoe. So any weight that comes onto the sonotube is then transferred onto a larger surface area at the bottom, so it doesn't sink into the ground. So it acts as two things. Stops it from sinking into the ground, but also stops it from heaving out of the ground. So those Bigfoots, in my opinion, are a must on any kind of a deck, especially when you're close to a sidewalk or a driveway. If you have a sonotube close to a sidewalk or a driveway, you take the snow off. Snow is insulation, so the snow will actually stop the frost from going in the ground as deep, right? But if you have a sidewalk, you probably clean it. If you have a driveway, you probably clean it. So what ends up happening is the frost goes deeper and deeper at those locations. So if you have a sonotube that's close to a driveway or a sidewalk, first of all, you'd want to have that sonotube go in a little bit deeper, and second of all, having a big foot on it and maybe 6mm poly wrapped around it to prevent it from heaving, because you know the frost is going to go deeper there. So plan. So whenever you're building a brand new house, you got to kind of think ahead. You think somebody might put a driveway there, or will somebody put a garage there? So if the deck's close to where you might have a garage, put that pier deeper into the ground and try to protect it from frost by either membranes, Bigfoots, to stop that from coming out of the ground. And I guess that's it. Hopefully this helps. Don't forget, you got to do an online assignment on Brightspace. Look at the chapter notes, look at the textbook, chapter 9, and make sure that's done before Tuesday.